All right, can everybody hear me out there? Someone can type into the chat interface. Let me know if you can hear me. Okay, great. I'm seeing a lot of yeses. Thank you so much. Okay, well, welcome to the second day of this two-day lecture series. So we're going to continue our investigation of software-level attacks on architectural and microarchitectural state. So here's a summary of the last lecture, what we covered yesterday. So we saw that buffer overflows let attackers overwrite code pointers that are in the path of the overflow. And so if we have the setup that we see on the left-hand side of the slide, we're basically looking at the top of the stack for a vulnerable process. We see at the very top of the diagram, here's a calling frame that then is going to invoke another function, which is the one that the attacker is going to exploit. In that function that is exploitable, we have an overflowable buffer. When the buffer overflow occurs, bytes get written going upwards in memory. Remember that the stack goes down, but the buffer has increasingly large indices going upwards in memory. And we see that as a result of the buffer overflow, a return address gets overwritten on the stack. Subverting control flow like this allows an attacker to do a couple of different things. So one thing that the attacker can do is what's known as a return to attacker provided shellcode. So the attacker can overwrite that return address on the stack and have it point to a location in the overwritten buffer. Why is that helpful? Because if the stack is executable, then the attacker could have filled that buffer with X86 instructions, with the shell code that's going to do malicious things like, for example, open up a command shell that then allows the attacker to send and receive arbitrary commands and responses via a shell that runs with the privilege of the exploited program. We also looked at attacks called return to libc, or more generically, return to some other pre-existing function. So in a return to libc attack, what the attacker does is overwrite that return address on the stack with the address of exit or some other helpful function that already exists in the libc code that's included in the library. The nice thing about return to libc attacks is that they don't require the attacker to inject any code into the stack. Instead, the attacker just diverts control flow to a pre-existing function, but invokes that function sort of at a time and a place that's unexpected to the program and ends up achieving attacker goals. Last lecture, we also looked at a bunch of defenses against buffer overflow launched control flow attacks. One of those defenses is a stack canary. So you can put a canary in between an overflowable buffer and a vulnerable return address on the stack. The stack canary will be checked for corruption immediately before a function returns. And so a canary doesn't actually prevent a return address from being overwritten, but it actually keeps a subverted program from using that corrupted address, from actually jumping to the location indicated by that corrupted address. We also looked at this technique called NX, no execute bits. This is essentially a new page table protection, which prevents the injection of executable code on a stack frame. The basic idea is that if we have a page that is writable, we don't also want that writable page to be executable. And that'll prevent the sort of straightforward shellcode injection in the buffer that we discussed in the last lecture. We also discussed some techniques which use randomization to make the attacker's life more difficult. So ASLR, Address Space Layout Randomization, involves the operating system placing the stack, the heap, the code, the static data in different places every time a program launches. This prevents the attacker from figuring out the locations of things once on a version of the program that's loaded on the attacker-controlled machine, and then being able to use all of those discovered addresses when attacking arbitrary different instances of the program on different machines. Struct randomization is kind of the same idea. So, given a C or C++ style struct, you can ask the compiler to place struct fields at a different offset every time the program is compiled. Once again, this also makes it more difficult for the attacker to generate a priori knowledge of where stuff lives in memory. So given these defenses, attackers have to step up their game. So attackers have to find mechanisms to do a couple of different things. First of all, the modern attacker needs some type of mechanism to read memory. Why does the attacker need to read memory? Well, to locate program state. As we'll see later, memory read disclosures are a type of vulnerability that are very helpful for allowing the attacker to de-randomize an address space. Because if the attacker can find the location of addresses in memory, then that actually helps the attacker understand where other things live in memory. Attackers also want the ability to write memory in a non-contiguous fashion. And the reason why this is helpful is that the attacker will want to avoid corrupting canaries. So with the vanilla buffer overflow, the goal of the attacker is to overwrite the return address, but there's a lot of collateral damage. So you have to write everything from the start of the buffer all the way up to the return address. It would be ideal if the attacker had a way to issue more pinpointed writes so that in effect the attacker could jump around, skip around parts of the stack and only write the parts that need to be controlled, like the return address. And finally, the modern attacker wants some type of way to implement arbitrary malicious behavior using only pre-existing code. So why is this only pre-existing code part important? Well, as I mentioned a couple minutes ago, no execute bits prevent the attacker from being able to inject new code into the program. So the attacker is restricted to executing pieces of code that are already in the address space. But are those pieces of code, are they Turing complete? Is it possible for the attacker to stitch those little pre-existing pieces of code together to perform arbitrary malicious activity? As it turns out, the answer is yes. And later in this lecture, we'll talk about return-oriented programming and jump-oriented programming, which are state-of-the-art techniques for allowing the attacker to implement Turing-complete behavior without actually injecting any code into an address space. Okay, so let's look at the magic of V-pointers. V-pointers, as it turns out, are going to be the key that unlocks a great many number of magical attacker abilities. So what's a V-pointer? Well, in a modern language like C++, Go, Java, C#, or Rust, all these languages allow the binding of an abstract method declaration to multiple concrete implementations of that sort of abstract contract expressed by the method declaration. So for example, in C++, there's polymorphism. In languages like Go, Java, and C#, you have this notion of interfaces. A single interface method can be implemented by multiple different instances of a particular class or a particular sort of interface satisfying type. And at runtime, the system has to determine which of the concrete implementations should be executed. Like most things in computer science, these types of abstraction layers, they're enabled via indirection. So, for example, in Go, you can have a type that implements an interface. The code which uses an instance of some object is going to interact purely with that abstract interface, but through a layer of indirection. At runtime, we figure out which sort of concrete set of instructions should be executed. This is all very convenient for the attacker because by corrupting those indirection tables that help to implement this indirection, the attacker can create memory exploits, both read exploits and write exploits. So let's look at an example here. We're going to look at an example in C++, and we're going to look at an example that involves polymorphism. So we are going to use the classic polymorphism example of animals. So we're going to create an inheritance hierarchy that involves animals. So first we have the superclass. It's of type animal. let's imagine that it defines some int ID field, and it also defines a virtual method, so get noise. So all animals are going to be able to return a string which describes what kind of noise they make. So then we have an octopus. The octopus class is a subclass of the animal class. It overrides that get noise function, and it just returns the string blub. I actually don't know what type of noise octopuses make, but let's just assume that it's blub. Now, we're also going to define a seahorse subclass of animal. It's also going to override that get noise method. Here I've had the seahorse declare that it makes a noise of WTF. I've actually picked two very bad animals for this example. I don't know that any of them make noises. I should have shown some forethought there. Anyways, you go into war with the slides you have, not the slides that you want. So we have this inheritance hierarchy here. And imagine we had the following code somewhere in the program. So we've got some function f. It is going to declare a new octopus object on the heap. Then it's going to declare an animal pointer, but it's going to actually make the animal pointer point to the octopus object. So this is all the magic of a polymorphism. And then the code is going to call a.getNoise through that pointer. And so what we would expect here is that we're going to retrieve the noise that's associated with the octopus. So how does this actually work behind the scenes? Well, behind the scenes, implicitly, this call to get noise becomes an indirect call through the v pointer for the octopus instance that's pointed to by the animal pointer. So that can be a little bit confusing. So let's look at a diagram. So off here to the left, we're looking at the virtual address space of the program that we're eventually going to exploit. So off to the left, we see there is the code segment. And somewhere in the code segment, we're going to have the implementations for get noise as provided by both the octopus class and the seahorse class. Somewhere in the static data section, we're going to have the vtables for the two classes. So you can think of the vtables as basically being this level of indirection, and each vtable is going to point to the functions that are associated with a particular class. So there's one octopus vtable. It points to all the functions that are implemented by octopi. And then there's a seahorse vtable, and that points to all the functions that are implemented by seahorses. So if you look up on the stack near the top of the diagram, we see two local variables, O and A. Those correspond to the pointers that we declared inside of function f. And those pointers point somewhere in the heap to that instance of the octopus. That is the memory that was allocated by the call to new. We see that the heap representation of the octopus has two things. It's got the ID, and that makes sense. That was sort of the field that was defined by the superclass of animal. But then we've got this v pointer too, that's inside the memory representation of octopus. So why is that helpful? Well, that v pointer is going to point to the vtable for octopus. And so what this means is that when get noise gets called at runtime, the way that we can determine which get noise implementation we need to execute is we basically go through the v pointer to find basically this table of function pointers that's going to tell us here's the concrete implementation of this virtual method that we need to execute. Okay, so let's imagine that the attacker has an overflowable buffer that is immediately before the octopus object on the heap. So imagine that there's a buffer overflow, and now the attacker is able to corrupt the v pointer and make it point to the seahorse vtable. Okay, so this is a corruption, right? Because the object that's in the heap, that's actually an octopus object, but we've corrupted its v pointer so that now that v pointer points to a seahorse vtable. So this is what's known as a type confusion, okay? And the reason this is a type confusion is because we've corrupted the runtime information that's necessary to make polymorphism work correctly. And so in this particular case, what we see is that when we look at this polymorphic method here, a arrow get noise, then this is going to result in the octopus object invoking the seahorse method, right? And the reason this will happen is because the V pointer for the octopus object has become corrupted. So in this case, the octopus is going to make the seahorse noise. Now you might be thinking, okay, so I said WTF instead of blub, like who cares? This is not a big deal. And in this particular trivial example, this is true. It's not a big deal, but in general, type confusion is very, very bad. Okay, type confusion is a very commonly exploited vulnerability avenue that can unlock a variety of additional evil powers. So let's go back to our animal example. Let's change it up a little bit. So now we are looking at the superclass of animal once again. It's going to define an ID, just as before. Now it's going to define a serialized method instead of a get noise method. So this method is a little bit more interesting. So it's going to take in a character buffer. It's going to take in the length of that buffer. And what the serialized method is going to do is basically return the bytes that are in the low-level representation of an animal object. And this might be useful if you're trying to, write binary representations of these objects to disk or send them over the network or so on and so forth. So now we're going to have the octopus subclass of animal. What we see here is that the subclass defines an instance variable of its own, a mindset. The mindset of the octopus is very simple. It's evil. I don't know if you know this, but octopi are very smart. They're very skilled at escaping from confined areas. They have many, many arms too, which I just don't trust intrinsically. So each octopus instance declares a mindset. Then it declares a serialized method. And so what's the serialized method going to do? Well, it is going to basically do a mem copy into the buffer that's taken in as an argument. The source is going to be the this pointer, the pointer to the memory that represents the octopus. And then we're going to use as the length this S value here. S is being set up here to the minimum of the length that's passed into the method and the size of octopus. So this is actually the right thing to do, right? Using this men thing here. So there's not actually a buffer overflow vulnerability in this particular set of code. And if we look at what the seahorse does, so the seahorse also declares its own type of instance variable, facts. So this particular fact is that the movie Aquaman is actually quite good, although the DC movie franchise is otherwise terrible. That's true. If you didn't like Aquaman, I'll fight you afterwards. It's a ridiculous movie, but it speaks to me. So each one of these seahorses has a facts variable. Now note that the facts array is of size 128. And note that mindset, that array is of size 4. This will become very important later. Now, the seahorse class also overrides the serialized method. And so the implementation of serialize here looks very similar to what it looked like for the octopus. The only real difference is that when we're trying to calculate this minimum size here, we just use size of seahorse instead of size of octopus. But otherwise, everything looks the same in these two different implementations of serialize. But once again, remember that these two member variables here, mindset and facts, they're of different size. This will become important. Okay, so now imagine that we had the code shown at the bottom of the slide. So we get a character buffer of size 1K. We declare a new octopus. We make it be pointed to by a pointer O. We declare another animal pointer, make it point to the same memory that's pointed to by O. Then we call a arrow serialize. So what's going to happen here? Well, if we look off to the left, the top left of the slide, we'll see the stack. This is exactly what it looked like before. So we've got the O and the A local variables. So both of those are going to point to an octopus that lives somewhere in the heap. In the heap, we've got a memory region that contains the V pointer for the object, the ID, and also that mindset array of size 4 that is defined specifically by the octopus class. And then we have sort of the vtable setup and the code setup that hopefully should look similar to what we discussed a couple slides ago. Now, let's imagine that we had a buffer overflow, right? Not in the implementation of serialize, because like I said, the implementation of serialize actually tries to be very careful about not overflowing any buffers or doing any reads that are too big for the size of a class. But let's imagine that beneath the allocation for the octopus object on the heap, there's an overflowable buffer. So the buffer overflow occurs. The v pointer gets switched similar to before. So now the v pointer for this octopus object is now pointing to a seahorse vtable instead of an octopus vtable. So why is this a problem? So this is a problem because the sizes of these two objects are different. So the size of an octopus I've shown up on the left-hand side of the slide, it goes from, it's in the range that I'm showing you right there. But remember that these two classes create instance objects of different sizes, right? Because fax is 128 characters and mindset's only 4. So what's the size of a seahorse? It's actually much bigger, okay? So what does that mean? That means that the call to serialize through this ostensible octopus pointer is actually going to result in a memory disclosure when we call a arrow serialize. And the reason is because the mem copy inside the seahorse version of serialize is going to read more memory than it should, because the actual type of A is octopus. It's not actually of type seahorse. So these types of, I should not use that word too much. These kinds of type confusions are very helpful because, as I've mentioned, they allow memory read or write primitives in many cases. So attackers will often use the kind of type confusions that I just showed to generate these out-of-bounds memory accesses. The thing that we just looked at on the previous slide demonstrated a memory read vulnerability. So the vulnerability allowed the attacker to read more memory than the attacker should have been able to read. Type confusion vulnerabilities can also generate memory write vulnerabilities. So for example, if you assign to an object field via a type confused this pointer. So here's a simple example. Imagine that we had two different classes. Now we'll be good computer scientists, just call them foo and bar, everybody's favorite meta-syntactic names. So imagine that the foo instance, which I'm showing sort of in the blue, it has 4 fields in addition to a v pointer. So this is what you'd see like if you declared a foo object on the stack or in the heap. And then the bar instance is actually much smaller. So it only consists of a single field, field 0, in addition to a v pointer. So imagine that the implementation for foo had a method that looked like this. So we're going to set F3, set field 3 to a particular value that's passed in as a parameter to the method. And set F3 is very simple. It just sets field 3 to the value that was passed in. Imagine that later on in the code, we had a line which allocates a new bar object. Then it allocates, then it declares a pointer to something of type foo. And then there's a type confusion that arises. The details aren't important here. I've just used the conveniently named function name of type confused to indicate that, aha, here is a vulnerable function where the end result is that F ends up pointing to a bar instead of a foo. So now imagine that shortly thereafter, the program calls F set F3. So this is a non-contiguous write vulnerability. Why is it non-contiguous? Well, if we look in the upper right-hand corner of the slide, what we see is that there's going to be a write that's generated to the sort of offset of field 4 with respect to this pointer. But the two sort of intermediate values here in this sort of incorrectly assumed to be foo object, they're skipped over. They're not written. And so this is a non-contiguous write vulnerability because if this were a buffer overflow, then the attacker would have to overwrite field 0 and then the field 1, the field 2 to get to field 4. But with this non-contiguous vulnerability, we can just sort of skip ahead and just write to field for directly. And so these type confusions are very helpful if they enable these non-contiguous types of memory vulnerabilities. So non-contiguous writes are very helpful because they let the attackers skip over things like canaries. Non-contiguous reads are helpful because they can reduce the amount of unnecessary data that the attacker has to read in. So let's see. So I think that we will now, let's see, there's a question says, does it matter that the serialized method is called from an animal pointer rather than an octopus pointer? So the magic of polymorphism is that basically using this vtable machination, at runtime, we're able to figure out the subclass of animal to which the animal pointer points to. So the correct method will always end up getting called. Then there's another question here. So how easy is it to implement type confuse without harming any canaries? So I mean, the devil is always in the details. So every type confusion is sort of unique. Type confusions, as it turns out, are both sort of very common exploit vectors, but they're not typically as straightforward as I just described. And I'll give you another example of a type confusion in a couple of slides, maybe even the next slide, that's going to demonstrate how you can actually launch type confusions without actually doing a buffer overflow attack first. So hopefully we'll address this question in more detail in a second. Okay. Yes, so as I promised, type confusions can be triggered in many ways, not just via buffer overflows. It's amazing. I'm like a prophet for content that I created myself. So an example of this is CVE 2015-0336. So if you don't know, there is this big database of vulnerability disclosures. It's a CVE database. And all of the sort of bugs that sort of get discovered that have security implications, they get registered with CVE. And so the 2015 here indicates the year. And then the number to the right of the 2015 indicates sort of the ID of the particular vulnerability inside that particular year. So whenever somebody says, oh, you know, we've got a server that's vulnerable to CVE, blah, 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 you can always look up that string, that CVE identifier, and then get more information about the bug. So what happened in this particular bug? So it actually involved flash code. So what the bug involved was, imagine that you had a browser that supported the Flash plugin. Well, a page could include malicious Flash code that used a carefully crafted proto-inheritance chain to trick a browser into interpreting a vector as a net connection. So there was a type confusion here. Now, for those of you who are not familiar with Flash, that's good because Flash is the devil and it's actually going away very soon. But roughly speaking, you can think of Flash as sharing many similarities to JavaScript, sort of at the low level. JavaScript basically uses this thing called prototype-based inheritance, where instead of sort of a C++ style class hierarchy, code can basically define an exemplar object that defines all the properties that you would like, quote unquote, subclasses, instances of that class to implement. So, you know, I can define an exemplar object that has, you know, fields X and Y. I assign that object to the proto field of some constructor function, and then that means that all the other objects that are created using that constructor function will have the properties defined by that exemplar object. So long story short, the existence of this type of mechanism for inheritance makes JavaScript and Flash very flexible because you can just sort of define at runtime these new class hierarchies. But it can also be a problem if there's a bug inside the browser's implementation of inheritance maintenance. And so in this particular bug, malicious code could essentially create an exemplar object in a way that created a type confusion, right? So there is no buffer overflow here. So the code was able to convince the browser to interpret a vector object as a net connection. So why is that particularly bad? Well, vectors are basically windows into memory, right? So you can read and write to a particular offset, and that corresponds to a read or a write to the underlying memory. So in this particular attack, what the attacker could do is call a net connection method on this vector, and using this type confusion, the attacker overwrites the vector's .linked field. Why is that helpful? Because if you can overwrite the vector's linked field to be a ginormous value, then now you've essentially defined this ginormous vector, which allows you, the attacker, in your malicious code to read or write to a huge swath of memory. Okay, and this is a very common thing people do in type confusions too. So try to corrupt an array in some way, either overwrite its linked field or somehow replace the function that checks whether a read or a write is in bounds. And then once you've got that corrupted array, you can then use that thing to launch read and write memory vulnerabilities. Okay, so that was another concrete example of how you might induce a type confusion. But I now want to look at this other question, though, of how might we go about overflowing a heap object? That's kind of an interesting question. So what I've shown in the left is the setup we have from a couple slides ago. We see that there's going to be this buffer corruption here, right, on the heap, not on the stack. And as a result of that buffer overflow on the heap, the attacker manages to redirect the V pointer. So we look at this and you might think, okay, well, I got a question. How exactly does the attacker position that overflowable buffer on the heap beneath the vulnerable object? Like, it seems very unlikely that the attacker will just get lucky and just be able to, by pure chance, find out that an exploitable object with an overflowable buffer on the heap is right next to another object whose V pointer we want to corrupt or whose function pointers we want to corrupt, so on and so forth. So how does the attacker do this? Well, I have an answer for this, or should I say this evil world in which we live has an answer for us. So one way you can sort of position the buffer properly is using a technique that is delightfully called Heap Feng-Shui. So how does this work? So suppose that the attacker knows details about the heap allocation algorithm. Maybe the attacker knows that the allocation algorithm is deterministic. If you feed the algorithm the same series of allocation size requests, the allocation algorithm will return memory chunks that are in the exact same place, modulo address space randomization, changing the starting base for the heap. Maybe the attacker knows that the heap allocation algorithm uses a slab allocation. So in slab allocation, this is a helpful allocation strategy when you have programs that allocate a lot of objects of the same size. So what you can imagine is that before any allocation occurs, the allocator is going to create a big array where each array element is of a particular object size. So maybe one slab, all for objects of, let's say, 32 bytes. And so now when the allocator needs to generate memory for a particular allocation request, it can just check a bitmap, for example, find the first free slot in the slab, and then return a pointer to that address to the caller. So maybe the attacker knows information like the allocator uses a slab approach. Maybe the attacker also knows, okay, maybe the allocator, it creates large objects on page-aligned offsets. Why might that be? Well, as I discussed in the last lecture, a lot of times when you try to interact with the memory interface of the operating system, things need to be page aligned. And so many allocators will use the mmap system call to allocate objects that are larger than a page in size. So if the attacker knows that, maybe the attacker knows that large objects have to be aligned with the page boundary. So anyways, assume that the attacker knows some of these details, then what the attacker can do is leverage this knowledge of the allocator to place a vulnerable object next to an overflowable one. So let me give you a sort of simple example. Let's imagine that we had a deterministic slab allocator in a program. So the first thing that an attacker can do is that the attacker finds the program to exploit. And so at the beginning of time, let's assume that no objects have been allocated. Let's imagine that then in step 2, the attacker starts to allocate a bunch of objects, filling up the entire slab. So how might the attacker be able to get this power to fill up the slab? Well, for example, think of a web browser, right? A web browser loading a malicious page. That malicious page contains JavaScript that the attacker defines. So the attacker can just, declare a bunch of new JavaScript objects and sort of fill up memory. So now in step 3, the attacker is going to deallocate 2 objects. Now, because the slab allocator is deterministic, as we're assuming, the attacker knows the positions in which these 2 new slots are going to appear. So in this case, they're going to appear at the beginning of the slab. And then what the attacker can do is allocate an overflowable object, shown here in red, and then allocate the vulnerable one. So this is the one that we want to corrupt. And so what will happen? Well, what will happen is that as the heap overflow kind of goes from left to right, we're going to see that the blue object, the vulnerable object, is going to get overwritten. And so there's a bunch of different techniques that people have come up with to do Heap Feng-Shui. It's not just for web browsers. People have done Heap Feng-Shui, for example, on kernel allocators inside of Windows and Linux. So it's a very powerful technique for trying to make sure that exploitable heap overflows actually bleed over into a particular object that you want to be corrupted. Okay, so at this point, we are now going to discuss return-oriented programming. I'll pause here and just see if anyone has any questions about the prior material before we move on. All right, going once, going twice. Sold. All right, we're going to go talk about return-oriented programming now. So what's the basic idea behind return-oriented programming? Well, these no executable bits, they prevent an attacker from injecting new code that does evil stuff. And as a result, no execute bits are a very powerful defense. These are standard on modern chips and modern operating systems. But what if the attacker can create evil by chaining together snippets of pre-existing code? We've already gotten a flavor of this with return to libc attacks, where the control flow of the vulnerable program was diverted to a pre-existing function in the process. The problem there, though, is that it's unlikely that a program is going to contain a single function which does all the kind of evil stuff that the attacker wants to happen. So it would be nice if the attacker could actually create sort of arbitrarily specific pieces of evil behavior just by chaining together pre-existing code in the application. And return-oriented programming enables exactly this. So let's consider the following scenario. This scenario will start out kind of being contrived, but we will make it more realistic over the course of the next 10 or 15 minutes. But for now, let's imagine that we have a server program. So it's a network server. It runs on a 32-bit x86. So what this means is that function arguments are passed on the stack, not in registers. Think back to our discussion of calling conventions from the first lecture. Let's also imagine that the server program does the following. It's going to establish a TCP socket S with a remote client. So, client connects to the server, results in a socket being created on the server side. The server is then going to map standard in, standard out, and standard error to the socket using the dupe2 system call. So why might that be helpful? Because then if the server wants to write output to the client, this remote client connected via the socket, then the server can just call printf, right? And so since standard out has been bound to this socket, the printf is going to send bytes over the network to the remote client. Also, the server can read client input just by doing a gets, reading input from standard in, which once again has been bound to the socket, reading from standard in, placing those bytes in the buffer. Okay, so we all know what printf is. So what about gets? What's going on with our friend gets? So if we look at the man page for gets, what do we see? Well, in the description, the first thing we see is never use this function. That's pretty good relationship advice. So we're going to use it anyway for this example, just to sort of give ourselves a sort of easy introduction to how ROP attacks work. So what does gets do? So the man page puts it very well. So gets is going to read a line from standard in into the provided buffer, right, until either a terminating new line or end of file is hit, which is then going to be replaced with a null byte. No check for buffer overrun is performed. So this is why you're never supposed to use this function. So in other words, if what's being fed in from standard in is a very long string that doesn't have a terminating new line or EOF for a very long time, then the buffer that's passed into gets could get overrun. Okay, so let's imagine the following. So let's imagine that a machine uses no execute bits, but it does not use stack canaries or address space randomization. Okay, so we're going to start easy and then kind of make things hard. Now, note that we are saying that no execute bits are being used, so we can't just inject shellcode here. So we're using no execute bits, but there are no stack canaries, there's no address space randomization, and let's imagine that the server application contains this code. So we've got a function called read request. It contains a buffer, and it calls gets on the buffer. This is a buffer overflow, doesn't get any more pure than this, right? All we do is declare a vulnerable buffer and then make it so we can overflow that buffer. This, American efficiency right there. And then imagine that somewhere in the code for the server, we have this run shell command. So what's it going to do? It's going to call system and then pass in the string /bin/sh. So that's the path to the shell, by the way. So what are the semantics for system? Well, what it's going to do is that system is going to spawn a new process with fork, and then it's going to use an exec system call to overwrite the child with a process that is going to take in as an executable the shell, and then we're going to ask the shell to execute a command, right? So what command are we going to ask it to execute? Well, it's going to be this command that got passed into the system call. So in this case, we're forking off another process. We're execing a shell there. What command are we asking the shell to execute? Just create another shell, okay? And so what system is going to do is it's going to wait for the child processes to complete execution. So think of this as sort of like a synchronous call, right? So when you execute system, it's going to spawn this new shell, and then the system command in the parent process doesn't return until the shell terminates. And so an important thing to note here is the spawn processes are going to use the parent standard in, standard out, and standard error due to fork plus exec semantics of how file descriptors get preserved across those two calls. Okay, why is this in the program? This is such a tantalizing piece of low-hanging fruit for the attacker. This is amazing. If only every program would contain a function called run shell. Like I said, we're going to make things easy for the attacker at first, and then we're going to make it more difficult. So anyways, just imagine for now that this network server has a function called run shell in it. Okay, so we might have the setup that we have over here. So we've got the read request function, and then we've got run shell. Now note that read request does not actually invoke run shell directly. Okay, so you can imagine that read request gets triggered whenever a new incoming client connection gets called to bring in some input, but read request never calls run shell. So we've got the stack setup that I'm showing sort of in the middle of the slide. And so what we know is that there is a buffer overflow vulnerability here. So we know that if the attacker's goal is to take control of a shell, then what the attacker can do is just overwrite the return address with the address of run shell, and then Cthulhu wins, right? So why is it that the attacker can know what the address of run shell is? Well, right now we're assuming that there's no address space randomization that's taking place. So the attacker can just load the program on his or her machine, figure out where run shell is on the local machine, and then just use that address in the attack payload. So why is this sort of like a total victory for the attacker? Once again, remember that this shell that gets spawned by run shell, it's going to have its standard in and out and error bound to the socket that is connected to the attacker controlled machine. So once this buffer overflow occurs and read request returns to run shell, then now the attacker can just send commands to the shell over the socket and then receive the output over the socket too. Okay, so let's make things a little bit more difficult. So now if we look at the bottom, we don't have a command called run shell. Okay, presumably that intern got fired, doesn't work there anymore. So now we have a function called run ls. Once again, maybe this is like a lazy programmer. They don't want to directly read the directory. They're going to use system once again, passing in the command string bin ls. And then if this function ever gets called, we're just going to run ls in a shell. So we don't have a direct call to system passing in the argument /bin/sh. But apparently the intern had one final act of revenge before they left. We do see that there is global variable somewhere called bash path, which contains the string /bin/sh. So it's not being passed in to run ls, but this string it exists in the address space. This should intuitively make us feel very uncomfortable. I will now make that uncomfortableness concrete. So imagine that we have a buffer overflow, goes from the bottom to the top as we've seen before. So what might the attacker put in the overflow payload? So in this case, the attacker is going to overwrite the return address for read requests with the address of system. Once again, because there's no address space randomization, we assume that the attacker knows what that address is of system. Here's where it gets interesting. So after putting the address of system here, the attacker is going to put a junk return address for system, and then the address that's inside this bash path here. In other words, this is going to be the address. This thing is going to point to the string /bin/sh. So why this funky setup here? What good is that? Well, if we look at sort of this bracketed region, note that this is what the system function expects the stack to look like at the beginning of the execution of the system function. In other words, system is going to expect that, when its first instruction starts executing, the top of the stack is going to be the place where system should return to, and then immediately beneath that is going to be the address of the argument that that system should consume. Remember, we're assuming this is a 32-bit X86, so arguments are passed on the stack. So this is actually pretty crazy, right? Because when read request returns, the top of the stack is going to be here. We're going to ret into system. System will start executing. The top of the stack will be here. System will find the argument that it should sort of pass to the shell that spawned. Well, that argument, it's going to point to /bin/sh, and then a shell is going to be opened up. So once again, Cthulhu wins. So that's kind of clever, right? So even though we didn't actually have a direct call to system and then passing in the string of bin sh in there, the attacker was still able to sort of corrupt the stack in a way that had the same effect as that first attack that I just showed. Okay, so now let's imagine that the string /bin/sh isn't in the program at all. What happens if this is the case? We might be thinking, well, okay, maybe attacks are impossible. And that's false. Attacks are very possible, like very, very possible. In fact, let's go do it. I mean, don't do this in real life, but let's do it in this imaginary criminal world that I've apparently brought you all into. So let's imagine that we don't have this helpful copy of the string bin sh sitting in memory. We still do have this run ls program here. It does still call system. So we know that system has to live somewhere in the address space, because if run ls is going to work, libc has to be in the address space somewhere. So the buffer overflow happens once again. So what is the attacker going to do now? Well, the first thing that the attacker is going to do is going to look very similar to what I showed you in the last attack. So we're going to overwrite the return address with the address of system. The attacker is going to put a junk return address for system here. Why is it junk? Because, you know, in this attack, we don't really care what happens after the shell terminates and then the system returns. The attacker's already stolen the data they want or whatever. And then we're going to put the address of the argument string right here. But I just told you that that string doesn't exist anywhere in the program binary. So where is this going to point to? Are you ready for it? It's going to point to somewhere on the stack, right? So the overflow allows the attacker to control the contents of the stack. So this address that we put right here can just point to the very next location in the stack, which the attacker has conveniently overwritten with /bin/sh. So what do we see? Once again, the attacker has set up a stack sort of configuration that is reasonable for system to consume. This is what system would expect the stack to look like during the first instruction that system executes. So once again, Cthulhu wins. So this all seems very horrifying. At least when I sort of learned about this for the first time, I was like, man, people are really creative in an evil way. And, you know, I learned about this in, you know, one of my classes. I said, well, surely it can't get any worse than this. And it never stops, though. That's just the lesson. It never, ever stops. I'm not going to let it stop for you. It's going to continue. So let's move on. Let's imagine that the attacker now has slightly grander goals. So now the attacker wants to call system, passing in /bin/sh 2 times. The attack that I showed you before only allows it to be called once, but let's assume that we want to call it twice. All right, let's assume that the attacker knows 3 addresses. First, the attacker knows the address of system, which we're assuming is possible because we're not using address space randomization. Now let's assume that the attacker knows the address of the string /bin/sh. The attacker knows this address either because that string just naturally exists in the static data somewhere, or if necessary, the attacker can just push that string onto the stack. So we know that the attacker will know where that thing is. And let's also assume that the attacker knows the starting address for this particular block of opcodes, okay? So we're gonna pop the top of the stack into EAX, and then we're gonna return, okay? So return is gonna pop the top of the stack and then put it into the instruction pointer, right? So this is how we actually vector control to a different place in code when a function returns. So a block of opcodes like this is called a gadget, right? It's not a function. It's just a small set of instructions that end with a ret. And as I'll discuss in more detail later, there are very user-friendly tools to discover gadgets in a binary. So there are these automated tools like ROP Gadget, which we'll look at in a second, which can just take in a binary that you have sitting on your local machine, and it'll tell you, oh, here are all the very interesting gadgets that are sitting in that binary. Okay, but let's assume that the attacker knows these 3 addresses. The address of the system, libc call, the address of the string /bin/sh, and then the starting address for what's known as a pop gadget. So we pop something into some register, then we return. Okay, so let's suppose that a machine uses no execute bits, doesn't use stack canaries or ASLR. It contains the code I show you on the left. So just for convenience, I've allowed the string /bin/sh to live in the program. That's not fundamental. We can get around that, like I said, by pushing the value of that string onto the stack. But to make things simple, let's just assume that the string exists naturally. Once again, we've got this run ls a function which doesn't pass in bash path directly, but does call system. Okay, so as we've seen millions of times at this point, we do the buffer overflow, goes from bottom to the top. What is the attacker going to write on the stack this time? Remember, the goal is to be able to call system twice, right? Each time passing in the string /bin/sh. So the attacker is going to write something that looks like this. Now this is a bit subtle and a bit complicated, so let me just sort of simplify the diagram. We're going to ignore RBP because it doesn't really matter for this attack. So here's what the stack is going to look like immediately before read request invokes ret. So in other words, read request has popped all the local variables off the stack. Now read request is about to invoke the ret instruction. What's that going to do? Well, the ret instruction is going to jump to the first instruction system, and then it's going to move the stack pointer up by 1, right? So we're like popping this address into EIP and then moving the stack pointer up by 1. So this is what happens at that point. And so now we are immediately after the ret in read request is executed. So at this point, the CPU is executing the first instruction in system, okay? So this is what system perceives the stack to be like. So when system finishes, it's gonna return to the address, this pop rat gadget here, and system's gonna find its argument right beneath that return address. Okay, so imagine that system has finished executing, and now system is about to execute its own ret. So what's gonna happen? So that ret is gonna pop the address off the top of the stack. That address is the address of the pop ret gadget. So we're going to have a situation that looks like this. So now we are inside the gadget. So the pop in that pop ret gadget is about to execute. So what's it gonna pop off? It's gonna pop off that argument that we passed the system. So it's gonna pop that argument, that pointer into EAX. Then it's going to result in a stack pointer that looks like this. So now we're in the ret portion of the pop ret gadget. And so what we see here is that the stack layout is going to result conveniently in system being called again with the argument of /bin/sh, right? Because we're in the ret part of the pop ret gadget. The ret is going to return us where? Well, it's going to return us to system, right? The stack pointer will move up again. Now we'll be in a situation where system will perceive that it has found a valid calling arrangement for the stack. And so this is a very powerful attack. Let's see here. So I see one question here. So a lot of the examples I've given have been around libc. What is the best alternative language in which to code an application that might prevent the largest number of attacks? Well, somewhat unfortunately, libc gets included in a lot of applications because even if, let's say you're writing, you're writing your program in Node, you're using JavaScript code for the application level code. Well, if Node uses C and C++ to internally implement all its functionality, then libc is going to be brought in. So as it turns out, a lot of gadget-oriented attacks will try to leverage gadgets that are in libc because libc is very large and it's a very common thing for a binary to include, even if that binary is not a native application. Even if you're using, some managed interpreted language, right? Like Python. If the interpreter is written in C or C++, chances are you're using libc under the covers. And so this is why, for example, like when you looked at that type confusion vulnerability for Flash, Flash code is it's not C, it's not C++. But basically, because there was a bug in the way that the Flash code was executed by the interpreter, you're able to tickle these bugs in the underlying C or C++ infrastructure. So that's why, managed code does provide a lot of advantages, just to be clear, right? I mean, with managed code, it's actually impossible for you to do something like a naive C or C++ level buffer overrun, because if, for example, you declare like an array in Rust or in Java, there are built-in checks to make sure that your read doesn't go out of bounds. However, if there's any type of C or C++ or handwritten assembly behind the scenes, then you can still try to trigger bugs in that infrastructure. Let's see here. So I see another question here. Basically asking about patches. So can a new OS aid in stopping attacks? Or will it be sort of like an iterative, sort of like repetitive game where there are new attacks that are being found, new patches come out, so on and so forth? So I think it is an iterative game. It is a cat and mouse exercise. As I'll show you in a couple slides, attacks are in fact getting more difficult to execute, which is actually quite comforting. So these defenses are making a difference. You know, the reason why we still see attacks is because, as I kind of mentioned in the first lecture, people are very smart. There are a lot of people on the planet, and you know, using the miracle of the internet, if one person discovers an exploit, then essentially all of humanity has discovered it. However, things are getting better, and I'll give you some concrete numbers to sort of show that in a couple slides. Okay, so one thing to keep in mind is that non-trivial programs have a Turing complete set of gadgets. Okay, so what I mean by that is that if you have a non-trivial program, and by non-trivial I mean, you know, 70K, something like that, then empirical research has shown that even very small programs, in terms of binary size, have a Turing complete set of gadgets. Why is that? Well, if you think about it, like, you know, even a very small program has a very large number of instructions. And furthermore, even if you have like a hello world program, how do you actually do hello world? How do you output to the display? Most likely you're bringing in libc. Libc is Turing complete several times over with respect to gadgets. So return-oriented programming is actually a pretty devastating attack that is feasible to launch on basically all binaries that are not toys. And as I mentioned earlier, there's actually a set of very user-friendly tools that allow you, the budding hacker, to figure out what kind of gadgets are in a program and how you might string them together. So I mentioned there's this one program called ROP Gadget. There are many others like it. This is a tool that lets you search your binaries for gadgets that are helpful for exploitation. So for example, here's what a screenshot might look like when you run this program on a particular binary. So let me call out some of the particular pieces of output here. So here in step 2, what this program is saying is that, oh, I found some gadgets in this binary that allow you to initialize the system call number. So in particular, if you're trying to use a ROP attack to invoke a system call, one thing you have to do is control EAX, right? So EAX is where the system call number is going to go. So, you know, system call number 0 might mean a read, system call 1 might mean a write, you know, so on and so forth. And so here, what this tool is telling us is that it found 2 very helpful gadgets. So this first gadget here is an XOR EAX, EAX, and then RET gadget. So why is that helpful? Well, remember from your binary arithmetic that when you XOR anything with itself, what do you get? You get 0. So what this gadget does is that this gadget zeroes out the register that the attacker is going to need to put the system call number into. So what does this second gadget do? This is an increment gadget. So increment EAX by 1 and then return. Why is this helpful? Oh man, well, if I can use this gadget in concert with the first one, then I can use the first one to set EAX to 0, and then I just repeatedly call this increment gadget till I've set EAX to be the number of the system call that I want to invoke. Yikes. So if we look at this output here, the tool is telling us that it's found some init syscall argument gadgets. So the arguments to the syscall are passed in registers. So what are these gadgets doing? They're popping something off the stack and then putting them into registers. So here we see a pop EBX and then a RET register. So in other words, if the attacker wants to set the value of EBX to some value, the attacker pushes that value onto the stack using the buffer overflow, and then makes sure that the pop EBX gadget gets called at the right time. And then that stack value is going to be popped into EBX. How convenient. We see there's a bunch of other gadgets here too, like a pop EDX RET gadget. That's convenient. And then the tool also tells us, hey, I just straight up found a syscall gadget, right? So right here, int 080, this is the way that you would call a gadget on a 32-bit Linux. And all this sort of works for 64-bit Linux as well, right? Same basic ideas. So that's pretty crazy. right? So you can use these automated tools to find out what gadgets are available. And in fact, these tools will actually construct the rock chain for you. They'll tell you, here's the set of gadgets to call in this particular order to get your chosen system call to execute. Now, one thing that makes it much easier for the attacker to sort of find gadgets is this thing called misaligned instructions. What does this mean? So the X86 ISA actually has variable length instructions. This is different from some other ISAs that have fixed length instructions. That's not true in X86. So the shortest instructions are 1 byte long. So like a no-op is 1 byte. Int3, which I think is the debugging interrupt generating instruction, that's 1 byte long as well. The longest instructions are 15 bytes long, as far as I can tell. And so that's actually pretty interesting, right? That you have such a wide variation in instruction length. I mean, when I hear about things like this, I think, oh, like Intel and X86, like X86 is like one of those ducks that's covered in oil and you're trying to wash the oil off. And it's like this, the oil just isn't washing off. And by the way, if you ever find yourself in possession of a duck or any other bird that's covered in oil and you need to wash it off, you can always go to the delightful site that is known as WikiHow. So WikiHow has a series of useless pieces of advice. There's actually a wiki article called How to Wash Oil Off of what looks like a heron or a pelican or something like this. None of the people in that picture are trained, but just know that like if you want to know how to do something incorrectly, WikiHow is there to help you. Anyways, moving on, we were talking about the X86 instructions and how long they are. So if you look in the voluminous Intel manuals, then you'll see where some of these links come from. So for example, some of these links come from the fact that you can add these instruction prefixes before instructions. These prefixes can indicate things like maybe you want certain locking semantics for memory operands that they manipulate. We'll see another concrete example of memory prefixes later in this lecture when we talk about some of Intel's control flow prevention mechanisms, or control flow protection mechanisms, excuse me. So what are the consequences of variable length instructions? Well, there are two consequences. One consequence is that a single instruction may span a word boundary. And a second consequence is that, so what does this mean? So like on X86 32, that means that the starting address for an instruction may not be divisible by 4 bytes. Similarly, on 64-bit X86, the starting address for an instruction may not be divisible by 8 bytes. So variable length instructions mean that a single instruction may span a word boundary. And also, this means that an attacker can try to redirect control flow into the middle of a compiler-emitted instruction. And it may be that if we jump to a misaligned offset, then there's actually an instruction there, or maybe multiple instructions that will successfully decode. And so even if the compiler didn't believe that it was emitting some category of instructions, using these misaligned jumps, the attacker can quote unquote discover instructions or gadgets that can be used for evil. And so here's a classic example that you see in a lot of the papers on control flow integrity and ROP attacks. So imagine you had this instruction here. So those bytes that I'm showing you correspond to the instruction and EAX with that constant over there. Now this is how the processor will decode those bytes if you start decoding here at this location, at the beginning of that sequence. However, if you start decoding here, slightly off of the beginning of that sequence, what do you see? Oh my God, it's an int 080. And so as I mentioned a couple times earlier, this is sort of the way that you invoke a system call on 32-bit Linux. So now let's look at a slightly longer sequence that we show at the bottom here. So in this sequence, we see a couple different instructions. So we see 6 instructions: a move, an add, 2 pops, and then a ret. Okay. So, if the attacker wants, the attacker can try to treat this entire sequence as a gadget, right? The attacker can try to divert control flow to the very beginning of the sequence, the 89 bytes, and then try to use this as a gadget. Now, the reason why shorter gadgets are typically preferable from the perspective of an attacker is that the bigger a gadget gets, the more side effects it has, right? And typically those side effects are bad because they're sort of collateral damage from the perspective of the attacker. The attacker just wants each gadget to do a very small number of things and complete. But the attacker could use this whole sequence here as a gadget. If the attacker jumps to the position I've shown here, then that actually becomes a call-based gadget. So it performs an add instruction, then it does a call. Similarly, if the attacker jumps to the location shown by gadget 3, then it becomes a gadget that allows an add, a pop, and then a ret. Now, it is true that not all misaligned offsets correspond to valid instructions. So for example, jumping into this range is actually going to cause the CPU to complain, right? The CPU is going to complain that basically this is an invalid opcode. It doesn't parse. So you can't be jumping around willy-nilly. But if you remember when I was saying that, even non-trivial programs have a Turing complete set of gadgets, this is another reason why. Because you can discover these quote-unquote new instructions at these misaligned offsets inside the program. All right. So what have we shown? So in a ROP attack, we've shown that the attacker creates a program whose execution is driven by the stack pointer. So as the stack pointer moves down the stack, which actually corresponds to upwards in memory, because remember the stack sort of grows down in memory and shrinks upwards. So as the stack pointer moves down the stack, the program executes gadgets whose code is pre-existing in the executable. And this attack can't be stopped by no execute bits. Why is that? Because we're not injecting any new code, right? The genius of the ROP attack is that we're just taking these tiny snippets from pre-existing places in the program to create this sort of arbitrary malicious behavior. Now you might say, but what about stack canaries, right? And what about ASLR? So the examples that I've shown you have conveniently assumed that those things aren't in place. Defenses like stack canaries or ASLR. Okay, so let's take a couple minutes and look at how you might defeat stack canaries. So there's a couple different techniques you could use. Here are a few of the most popular ones. Approach one is to harness non-contiguous writes. So as I mentioned maybe about 10 minutes ago, a non-contiguous write vulnerability allows the attacker to only write a particular location of interest. So if the attacker happens to know where, for example, a return address is, then the attacker can use a non-contiguous write to only overwrite that return address and not have to stomp over all of the stuff in between, the local variables and the exploited function, the canary, and then that return address. So type confusions are a common source of these types of non-contiguous writes. Now, of course, we're assuming the attacker knows the address at which to write. And so we're kind of assuming here that the attacker's already gotten past address space randomization. We'll deal with that in 1 second. But for now, suffice it to say that if you have a non-contiguous write vulnerability, and if you know where vulnerable code pointer is, function pointer, or return address on the stack, you can use that non-contiguous write to get around canaries. You can also use an approach called stack pivoting. And this approach is actually more popular as far as I know for getting around stack canaries. The basic idea is that the attacker needs to corrupt the register that is later used by the program to modify the stack. So for example, imagine that a program in its executable code had an instruction sequence like move RAX to RSP. So if the attacker can corrupt RAX such that RAX is now containing a value that the attacker has chosen, then when the program executes this instruction here, the program will change the stack pointer to a location of the attacker's choosing. And so if the attacker has also ensured that the place where the stack pointer is now pointing to contains a ROP payload, for example, on the heap, this is a very common thing to do. You pivot the stack pointer to point to the heap instead of the actual stack region. Well, then the sort of ROP attacks that I sort of showed you just work right off the bat, right? So you put the payload in the heap, maybe using some type of buffer overflow involving a heap object. You then do a stack pivot to make the RSP pointer point to the heap, and then you do everything else as expected, and then things just sort of work. Okay, now how might we go about defeating address space layout randomization? So usually what attackers try to do in modern state-of-the-art attacks is that the attacker tries to use a memory read vulnerability to find a single concrete memory address. And then using that single concrete memory address, the attacker tries to then discover other concrete addresses. So what's an example? If the attacker can discover a single code pointer to a function in libc, that's very powerful, right? Because what address space randomization does is it changes the offset of that big chunk of code belonging to libc. However, address space layout randomization does not change the relative orderings of function code inside of libc. So if the attacker can discover a single code pointer to any function in libc, the attacker could have calculated offline the relative offsets of other more interesting functions in libc. So as soon as the attacker finds out one concrete address for a code pointer in libc, the attacker can then leverage that knowledge of those offsets for other interesting functions in libc to then invoke those. Attackers can also try to use an overread of a buffer on the stack to disclose return addresses, right? So imagine that the attacker had a read vulnerability, not a write vulnerability, involving a buffer on the stack. So in this case, the attacker isn't trying to overwrite the return address with buffer overflow, merely find some addresses that are sort of on the stack. And if the attacker can do that, well, great, because now the attacker can narrow down the location of the stack. Let's see here, and I see a question. So can libc be recompiled to be randomized or position independent itself? So libc is position independent, right? So you can definitely map it into different places in the address space. The problem though is that position independence in and of itself doesn't actually change the relative offsets of individual functions inside of libc. So can libc be recompiled to be randomized? That's definitely possible. That's definitely possible. I don't think that's done very often for reasons that I'm not clear why that is. There might be some good reason for that. But yeah, it's definitely possible in theory. Okay, so those are sort of two sort of ways that people might try to use a memory read vulnerability to de-randomize the address space. Another thing that programs can do is basically try to leverage program-specific quirks that might leak information about where things live in the virtual address space. So for example, a program might load some libraries that are non-relocatable, right? Maybe whoever made the library is a doofus, and then it compiled a library to be position independent. So the library has to go into a particular place in the address space. It only takes one mistake like this. And people have actually showed how to exploit this. I'm aware, at least particularly on Windows programs, Windows systems, where there are some very old libraries that are not compiled to be relocatable. So as we've already discussed, even very small sort of chunks of code have a lot of tempting gadgets in them. So if you're an attacker and you know that a program uses one of these non-relocatable libraries, just try looking for gadgets there, right? You don't even have to work very hard to de-randomize the entire address space because you just have one chunk of it that you know is in a fixed location. Here's another interesting thing. So address space randomization doesn't change after fork. Remember the semantics of fork. So when you create a new process using fork, the child gets an exact replica of the parent's address space. So what does that mean? That means that the child gets the same address space random offsets that the parent had. So imagine that you had a process that the attacker could try to guess an offset for a particular function pointer, return address, or whatever. And let's say that the program crashed. The process crashes if the guess is wrong. Well, if what the parent process does is notice that a child has crashed and then use fork to spawn another child process, the new child has the same layout as the old one. So assuming that the attacker doesn't raise any alarms by repeatedly trying to guess locations, and assuming that the attacker does know maybe a little bit more about where things might reside, some hunch about, general regions, because a 64-bit address space is pretty big, right? The attacker can basically just sort of, pound a bunch of guesses at these processes. If the guesses are right, hooray, you've taken control of the program. If not, a child process crashes, a new one gets created, the attacker reconnects and then tries again. Okay, so that was sort of an overview of how people might try to get around stack canaries in address space randomization. I want to briefly talk about the difference between return-oriented programming and jump-oriented programming, sometimes called JOP. So in return-oriented programming, the stack is going to hold the addresses of gadgets as well as the input data for the gadgets. And so the stack pointer in return-oriented programming kind of acts like this weird program counter, keeping track of which gadget the malicious control flow should go to next. So we kind of have a setup that looks like this. So in the middle, we have the stack, top of the stack is pointed to by RSP. And so we have the addresses of all these gadgets. And then, in some cases, we have data for the gadgets that's also included on the stack. And so each one of these gadget addresses is going to point to some location in the code segment. So as I mentioned a couple minutes ago, the gadget addresses and the data can be stored in the heap if you can find one of those stack pivot gadgets, right? So if you can have something like a move REX RSP where that should be red, excuse me. So where the, no, that's correct. Never mind. So you have that gadget where you do a move of RAX into RSP, then you do a ret. And so if RAX is attacker controlled, then what ends up happening is you have a stack that's controlled by the attacker. So what happens in jump-oriented programming? So in jump-oriented programming, there's going to be a dispatch table that holds the addresses of gadgets as well as the gadget input data. And so you need this special dispatch gadget, which is going to increment this sort of gadget-based program counter. So imagine the code segment, you've got a bunch of gadgets, so 3 in this case, and we're doing jump-oriented programming. So note that all of these gadgets now, they terminate with the jump instruction, not with the ret instruction. And so then we have this dispatch table that may live in the stack, it may live in the heap, maybe a combination of the two. And so the dispatch table is going to hold, 2 things. It's going to hold some addresses. These are the addresses that sort of point to the gadgets that we want to execute. And then in the dispatch table, we're also going to contain some data for some of these gadgets. And finally, we're going to have this dispatcher gadget. So the way that the basic setup works is that after each one of these individual gadgets execute, every single one of them is going to return back to the dispatcher gadget. The dispatcher gadget is then going to do some stuff. It's going to terminate in a jump, and that jump is then going to go to the next gadget to execute. And so what's really nice about this setup is that the dispatch table, it doesn't need to be in contiguous memory, right? It can be kind of like scattered around. And the nice thing is that this dispatcher gadget sort of frees us from this tyranny that we had in the return-oriented attack, which is that all of the gadget addresses and the data, they had to be contiguous and they had to be sort of sitting beneath the stack pointer. But if you can find one of these dispatcher gadgets, okay, well then your life becomes somewhat easier as the attacker. Your life also becomes more convenient if you're the attacker, because if the system is only looking for ROP attacks, but it's not looking for JOP attacks, for jump-oriented attacks, you may be able to slip under the radar. So here in the upper left-hand corner, this is a real-life dispatcher gadget that's in libc. So we're going to add EDI to EBP, and then we're going to jump to some target destination based on the calculation. We'll read the value in EBP, subtract hex 39 from it. And so what the attacker has to do to make this sort of dispatcher gadget work properly is that before this jump instruction executes, the attacker has to correct for this sort of 39 here by basically using prior gadgets to massage the value in EDI. So EDI is what's going to be used in this particular gadget to set EBP. Let's see here. So I see a question here. So when using a buffer overflow to rewrite the stack for ROP attacks, filling it up with gadgets, isn't there sort of like a limit on the stack size? It is true that eventually you may run out of stack size if you may run out of stack space, excuse me, if you continue to fill up the stack with a bunch of gadgets. However, the stack is very, very large compared to the size of an individual gadget. Or excuse me, it's very large compared to the size of what you're pushing on the stack. What are you pushing on the stack? You're mostly pushing addresses, right? These addresses where you want gadgets to go to next. So that's going to be the size of, the word size. You have 4 bytes on 32-bit x86, or 8 bytes on a 64-bit x86. So so the stack size in practice is not a limitation on how people construct these attacks. Good question though. Okay, so here we've seen how the dispatcher gadget works. The dispatcher gadget essentially allows us to not have all of this data and gadget address information have to be in one contiguous place. And so I've showed you this real life dispatcher gadget over here. Okay, so here is a real life JOP attack that was launched using libc gadgets. So here we see this first gadget. It's going to use this pop A instruction. The pop A instruction is super helpful. Basically, the pop A, I think it stands for pop all, and it's going to load all of the registers using values from an attacker controlled stack. Okay, so we're assuming that the attacker has been able to take control of the stack, for example, maybe via stack pivot. The attacker pushes a bunch of values onto this the stack that's controlled by the attacker. Then the attacker starts the JOP attack. So the first JOP gadget is going to pop all of those registers from the attacker controlled stack into EAX and EBX and so on and so forth. The gadget is then going to do this CMC instruction, which will have no practical effect from the perspective of the JOP attack. Like, it actually will do things to the machine, but it's not actually going to impact what happens in the attack. Now, by the way, you can see this is one reason why shorter gadgets are preferable to longer gadgets, because the longer the gadget chain gets, either with ROP or with JOP, the more likely there are going to be these side effects that don't do the things that an attacker needs to have done. But anyways, in this case, the CMC instruction has no effect. Then we do a jump, and that's going to get us back to the dispatcher. Then we're going to have another gadget set of instructions. So we're going to do an exchange. This is basically going to swap the value of 2 registers. There's a division instruction, which has no practical effect on the attack, although it does make the machine do some floating point division. Then we're going to go back to the dispatcher. So now we're going to have the third gadget in the chain. We're going to set EAX. We have this move instruction that has no practical effect. Hilariously, this move instruction actually changes ESP. Aha, but we're using JOP, not ROP. So that's why it has no practical effect, even though now the stack pointer is pointing to God knows where. We end once again by doing a jump, in this case a call, back to the dispatcher. And then we just do sysenter. So what did the previous gadgets do? The previous gadgets were setting up the system call. So they were assigning to EAX, which is the system call number, and then assigning to the other registers, EBX, ECX, EDX, which correspond to the arguments to pass to the system call. So that's pretty neat, right? So we've used gadgets in a way that doesn't use return-oriented principles. So we're not doing, sort of like these ret terminated gadgets, but we still managed to achieve the same effect with the help from this dispatcher gadget. So all of this just sounds terrible, right? So all of this sounds like, man, there is so much cunning in the world. How could we possibly hope to defend against these attacks? But I do want to say it's actually not as bad as it seems. So as it turns out, a lot of the defenses that I've mentioned, particularly when you look at them in concert, it's making these attacks increasingly more difficult. So let's look at some of those defenses. In particular, let's go back and take another look at Intel's control flow enforcement technology. So if you like reading white papers, Intel is the company for you. There is a white paper you can look at. I think this one is about 350 pages. So if you got any small children there who you want to become good at literacy, you want to teach them how to read, just give them this and something's going to happen to them. So this document describes Intel's approach towards CET. We've actually already talked about one of the technologies that CET introduces. So it introduces two things, shadow stacks, which we discussed in the last lecture, and indirect branch tracing, which we'll discuss next. And the CET stuff, I mentioned this last lecture, it's already coming out in the Tiger Lake chips that arrived this year, and it's going to be in the upcoming Xeon chips as well. And AMD says that it's working on equivalent technology. So what this means is that in the near future, all x86 chips should support these two techniques, shadow stacks and indirect branch tracing. Okay, so what does indirect branch tracking or IBT do? So IBT is going to introduce this new instruction called in-branch. Now it's very clever the way that Intel encoded this is because this instruction actually evaluates to a no-op on older CPUs. So that means that if you try to compile a program and add the support for IBT, then if you run it on sort of like a pre-Tiger Lake processor, for example, no harm, no foul. The CPU would just interpret this in-branch as a no-op. So why is this new instruction useful? Well, it doesn't really do anything interesting in and of itself, but what the hardware is going to do is it's going to ensure that any jump or call target is an in-branch. So the in-branch instruction kind of acts as a indicator that this address is actually a valid target for a jump or a call. So imagine that we have this situation over here. So here I show you two basic blocks. So the first basic block, it's going to have this incoming edge here. Basic block starts with an in-branch. We have a bunch of instructions, then it goes to a jump. Here we have another basic block. It also starts with the in-branch, has some instructions, ends with a ret. So this type of control flow would be allowed. And the reason why this type of control flow would be allowed is because we see that the direction that we're going, we go to a basic block that starts with an in-branch. So that is allowed by IBT. Let's assume that we had another basic block over here. IBT would not allow this control flow that I just showed you, basically going from this jump here to this instruction here. Well, why is that? Well, it's because this instruction is not an in-branch, right? And so IBT gets paranoid about this because it says, oh my goodness, if you're not actually going to an in-branch, then maybe there's some type of a ROP or JOP attack that's taking place. So if this control flow that I've shown here with the little X were to actually happen, the hardware would actually complain. It would raise an exception and the OS would take over. However, this control flow would actually be allowed, right? Even though the in-branch in effect is a no-op, it doesn't do anything, this control flow that I just revealed makes IBT happy because it seems like there isn't a JOP or a ROP attack that's being launched. Now, it is possible that the compiler can actually prefix a jump or a call instruction with this special 3EH prefix. That means like no track. So this is an example of one of those instruction prefixes I was talking about before. So the hardware will ignore a jump or a call to a non-in-branch instruction if the jump or the call is prefixed with this thing here. But otherwise, it'll look for that in-branch thing. So how do you use IBT? So the OS needs to configure some registers. So there's this master enabled bit in the CR4 control register. There's a model specific register, IA32UCET, you have to turn on. And you also have to use a compiler that inserts in branch at each potential indirect jump target. So if you look at the documentation for GCC, all this stuff is here, support for both of these CET technologies. So if you compile with the FCF protection flag enabled, then if you set the branch bit, then you will enable IBT-based protections. If you set the return flag, you will enable shadow stacks, and you can actually enable both if you want to as well. And by the way, if we look at the bottom of this documentation, that option there, F-stack protector, that enables stack canaries. So, all these technologies I've been talking about with respect to defense, they're all there, and you can all use them, and they're being used right now. So if we look at indirect branch tracking, it's important to note that IBT, it actually provides relaxed CFI. So a given jump or call can go to any valid jump or call target. So what do I mean by that? So let's just simplify things a little bit. So let's say that we had the control flows that we show with the arrows right now. And so I'm showing that all three of those control flows, they are blessed with respect to IBT's perspective on things, because all of those control flows, they all end up terminating in an in-branch instruction. However, it could be that these two control flows at the top were developer intended, but this one here was not. So the developer didn't actually write code for which this particular control flow transfer is valid. However, because this basic block over here has an in branch at the top, IBT will allow this to happen, this control flow to occur, even though it's not developer intended. So that's why IBT provides relaxed CFI. So if you're the attacker, you might think to yourself, me gusta mucho. Because if you look at this stuff, you might say, well, maybe there's still a possibility to do ROP or JOP if the attacker can find enough in-branch preceded gadgets. And so I haven't seen any research on whether this is actually the case. Intel does admit, to its credit, that IBT is relaxed CFI, so it's not going to prevent all types of attacks. But suffice it to say, even though this is relaxed CFI, this does significantly raise the difficulty bar for attackers to launch these types of control flow attacks. Let's see, someone asked a question, Thomas, is there any good reason for not using these GCC options always? What are the potential downsides? Yeah, in general, you should be using these GCC options. There is going to be overhead with some of this stuff. So that overhead, though, is typically pretty small. So particularly with things like stack canaries, the overhead is very minimal. The overhead with a lot of the CET stuff is also minimal because you're having these protections put in and enforced by the hardware themselves. Now, I should say that some of the CET stuff is pretty new. So I think people are still trying to figure out what the performance implications are. But my intuition is they're not going to be that high for commodity workloads. And as I mentioned, I think yesterday, Windows and Linux, they're already looking at implementing these techniques and incorporating them into the respective kernels. So I think these techniques are the right thing to use in most cases. Let's see, I see some other questions. All of these attacks seem to take advantage of X86 specific features. Would it be more difficult with RISC processor architectures? The answer is yes, it would be more difficult with simpler instruction sets. I mean, Intel, they have to deal with a lot of issues of legacy code and backwards compatibility. This is one of the main reasons why a lot of their solutions seem like overly complicated, because Intel is actually trying to do some of their customers a favor and say, hey, we're going to allow your old legacy workloads to run on the fanciest Intel chips, while simultaneously we're continuing to introduce these new chip features. So yeah, some of these attacks do become more difficult on other architectures. For example, if you have an architecture that has fixed length instructions, then you don't have this misaligned instruction problem that I've mentioned before, because it's invalid to jump to arbitrary places in the code segment. So yeah, some of these things do become easier on RISC architectures. Okay, so as I was saying, even though some attacks are still possible, using all of these defensive techniques, IBT, ASLR, shadow stacks, and X-bits, stack canaries, they make it much harder for attackers to divert control flow. And so what do threats actually look like today? You know, over the past 2 days, we've sort of gone through a bunch of examples that increased in the sophistication of the attacks. So now let's actually take a look at, you know, kind of what the current state of the art looks like. This, by the way, is two people attacking each other at a Renaissance fair. And I saw this, I thought to myself, have these people ever heard about video games? You don't have to get on a horse and then attack another person with a pole to have fun. You can just do this stuff virtually online. I don't want to brag, but I was able to acquire a Nintendo Switch. It's pretty fun. I also got a Super Smash Brothers. But then yesterday, I literally got beat up by this character here. I have no idea what species that thing even is. I just know that I got savaged. It was violent, it was brutal, it was humiliating. And so I'm still recovering from this experience. And so maybe the right thing to do is to go to Renaissance fairs and joust with people on real horses. I don't know. I do know this discussion currently has little, if anything, to do with computer vulnerabilities. So let's move on and ignore the fact that I was annihilated by whatever it is that is gloating over my broken body. So there's this really cool talk that was given about a year ago by this guy, Matt Miller. And so he works for Microsoft's Security Response Center. And so he basically talks about the trends that Microsoft is seeing at a very large scale with respect to how attacks are taking place. And so he has a bunch of great graphs. And when I post these slides later on, if you look in the notes section, I'll have a link to this talk. So you can take a look at all this stuff. And I'll also include links to other supplemental information involving other pieces of content from the slides. So one thing that, that he says is that there are more vulnerabilities fixed and fewer known exploits, right? So this is very interesting. So on the left, he basically says, here's a graph of the number of CVEs by year. And so that number is going up. And so it seems like, well, at least at first glance, the risk appears to be increasing. But then if we look on the right, if we look at the percentage of the CVEs that are actually exploited within 30 days of the patch, that seems to be going down. So that's interesting. So that means that, like, at least intuitively speaking, we have a little bit of evidence to suggest that, you know, even though we're finding more and more exploits, people don't seem to be sort of exploiting each one of these CVEs as much as we might think. And that indicates that maybe these defense mechanisms are actually helping a lot. He then goes on to describe the types of exploits, and in particular, the type of exploit vectors that are actually being leveraged by attackers. And as the title of the slide says, memory safety issues remain dominant. Right? So this graph right here shows the relative prevalence of memory safety versus non-memory safety based bugs. And essentially it's 70%. 70% every year, those are the bugs that are going to use memory exploits. So this is hopefully why you can see why I spent so much time talking about various types of memory exploits, because this is the most popular way that programs get exploited today. Now, if we drill down into the root causes, this graph is super interesting. So basically what this graph is showing is it's showing across time on the x-axis, sort of like a histogram, if you sort of read per year, of the most popular types of attacks. And so what we see is that sort of vanilla stack corruptions, sort of like your very sort of, you know, easy, naive buffer overflow in the stack. Well, as this slide says, those types of stack corruptions are essentially dead, right? Because of stack canaries, and things like that. So you will see these kind of exploits from time to time in server and desktop software. You'll see them much more frequently on IoT software, which generally happens to suck. But the vanilla sort of buffer overflow in the stack is basically toast. So what do you see a lot of? Well, we've talked about some of this stuff in the past 2 days. So we see the number 1 and the number 3 most popular vulnerabilities are heap out of bounds errors and type confusion. And so we've talked about how in type confusion, you can basically use it to create these non-contiguous reads and non-contiguous writes. So, in this lecture today and yesterday, you've actually learned about some of the most common current attack vectors. And so this slide here is also very interesting. It basically says, here is the general set of high-level steps that many attacks have followed since 2016. So I love following directions. It says start over here, and so we shall. So what happens is that in many of these attacks, you place an array at some known location, or at least some predictable location in memory. Then you modify somehow the base of the array, the length of the array, such that now you can use this array to perform read and writes. So we've talked about that today. I gave you that example of the flash vulnerability, where there was a type confusion that was used to essentially turn a vector into a vector of essentially infinite length, meaning that you could read and write from the vector and therefore read and write arbitrary places in memory. So many attacks start like this. You try to find some type of array, and then you use that array to implement read and write vulnerabilities. And then what do? So then you can use those read or write vulnerabilities to discover addresses, right? So now what you're trying to do is you're trying to de-randomize the address space. And so you use that by leveraging the read vulnerability to find out things in memory. Then you construct the ROT payload, right? By searching for code sequences in the dynamic library, the static library, wherever. We've also talked about how to do that. As I mentioned, there are tools that make this aspect of it very easy. And then once you have the ROT payload, you can do a bunch of different stuff. So you can corrupt the return address to trigger the return of the first gadget. You can corrupt a function pointer to trigger a function call to the first gadget. You can corrupt C++ vtable pointers to trigger method calls to the first gadget. All these things lead to executing the ROT payload, and now you're executing arbitrary native code, and now you're at the end, right? So hopefully you can see that over the past 2 days, we've actually covered a lot of the steps in these types of attacks. So if you understood how this stuff works, you're well situated to go in and do deep dives on some aspect of this flowchart that you find particularly interesting. Okay, so for the last part of this lecture, we are now going to do a sort of exploration of SGX. Okay, the beast known as SGX. So SGX is pretty interesting, and I think SGX actually represents the future of where a lot of security research is going to go in the future, namely trying to leverage interesting new hardware primitives to provide some type of better isolation guarantees. Because I think that with the the death of Moore's law and all kinds of scaling laws, you're going to start to see more chips that don't have better clock speeds. And, many applications are not, particularly very parallel. So you might think, okay, maybe we can use some of these cores or some of this die area to do security stuff. So I'm going to give you an overview of SGX and some of the challenges. Because like I said, even though SGX has been found to have some problems, I think SGX is a move in the right direction. I'm actually pretty excited to see more security concerns coming out in the hardware community. Okay, so here's a sort of quick overview of SGX. The first goal is to allow a client to interact with a secure server-side computation. So we assume that this is going to be a data center scenario, and we're assuming that the OS and the data center operator are untrusted with respect to the client that wants to interact with some server-side computation. So we want to prevent both the OS on the data center machine and the data center operator themselves from reading the state of the secure computation or tampering with it in any way. And we also want to prevent the tampering with that state without being detected. And so the second goal of SGX is that we want to allow the secure server-side computation to execute atop the highly optimized circuits which execute traditional computations. So what do I mean by this? Well, you know, the architects at Intel put a lot of effort into making the microarchitecture fast. And so ideally, we would like this secure server-side computation to run to the greatest extent possible on those highly optimized circuits that do things like speculative execution and out of order execution, you know, so on and so forth. So, oh no, this immediately raises the specter of side channels, right? Because if we're not going to have a separate chip that's going to execute this secure computation, then presumably this means that there's going to be some sharing, if only at the microarchitectural level. And so as we'll see later on, there are in fact side channels that emerge. And there's also this like very big challenge of just sort of, you know, if you're going to be a hardware designer, how do you add a minimal set of SGX hardware components to a complex legacy microarchitecture? So we're going to look at these issues over the next couple slides. So here's what a 64-bit X86 address space looks like. This should hopefully all be review for you at this point. At the top, we have the kernel mode state. At the bottom, we have the user mode state. And so in SGX, what we're going to do is we're going to put the secure computation, which is called an enclave in SGX terminology. We're going to put it at the bottom in the user mode state. And so inside that enclave, we're going to have essentially the stuff that you would expect, a stack, a heap, static data segment, some code. There's also going to be an entry table, which is going to help to coordinate how external code jumps into or invokes enclave functionality. So as this diagram kind of suggests, there's going to be this untrusted host process which embeds an enclave. And so when code in the untrusted host process is executing, so this is the code that's sort of down here in the very bottom left of this diagram. So when code in the untrusted host process is executing, it can't access enclave pages. If you try to read, you're going to get this like special value -1. I mean, I shouldn't say -1 is special. We all have a -1 in our life. But you will always get -1 regardless of what the state is of the actual enclave pages. And if untrusted host code tries to write to the enclave pages, the hardware just drops those writes. So the untrusted host, the way that it interacts with the enclave code is using this EENTER instruction, which sort of tells the hardware, hey, I'm the untrusted host. I now want to start executing in enclave mode. So the enclave code, it's interesting. It's going to run at ring 3, which is the least privileged level. However, the enclave code can access the entire user mode address space of the host. So in other words, the enclave code can access all of this stuff in the bottom part of virtual memory. This is helpful because, as it turns out, the enclave code cannot issue system call instructions like syscall or int. So that means that if the enclave code wants to issue IOs, it has to rely on that untrusted host. So for example, like if the enclave wants to write data to the disk or to the network, it has to place that data somewhere in the memory that's accessible to the untrusted host, and then basically hope that the untrusted host will perform the write. Similarly, if the enclave wants to read data in, then it has to put that data request somewhere in the memory accessible to the untrusted host, and then ask the untrusted host to issue the IO, and then read that result in from the untrusted memory. And the enclave can return control of the CPU back to the untrusted host by executing this new EEXIT instruction, enclave exit instruction. Okay, so let's drill down on the microarchitecture a little bit more. So we've got a core. It's going to have like an L1, L2, so on and so forth cache, CR3, page table pointer. It's going to have a bunch of TLBs, which control the mappings from virtual addresses to physical ones. Then we're going to add this special isEnclave bit. So you can think of this as being somewhat similar to the logical isPrivileged bit that the CPU has. So isPrivileged bit, that bit basically says, are we executing in kernel mode or not? IsEnclave that bit indicates whether we're executing enclave code. So we've got physical RAM, and in between a core and its memory hierarchy and the physical RAM, you've got this memory encryption engine. And so using the memory encryption engine, we are going to separate physical RAM into two separate regions, one of which is used for normal system memory, the other one of which is called the enclave page cache. So this is where all the enclave state lives. And so what the memory encryption engine is going to do is that when enclave code is running and an enclave owned cache line has to be evicted from the L3, then the memory encryption engine is going to transparently encrypt that thing and add some max and add some counters before sending that memory write out to the actual physical RAM. So this means that all of the EPC state, all the enclave page state, that's all encrypted. You know, so even if you were to, you know, use like double E tricks and try to like read that RAM directly, it's all encrypted by the memory encryption engine before it even hits the bus that goes to physical RAM. So it's safe against physical tampering. And so when enclave code is executing and it needs to bring in enclave data from physical RAM to the L1 through L3 cache, then as that cache line is coming from physical RAM, it's going to go through the memory encryption engine. That memory encryption engine is going to decrypt the data and then check the counters and the max to look for integrity and freshness. So SGX also adds this hardware-based data structure called the Enclave Page Cache Map, the EPCM. And so this EPCM is an SGX structure that's going to contain one entry for each page in the EPC. The EPCM can only be modified by SGX instructions. And that's important because the EPCM is going to contain a lot of important metadata, like, you know, which enclave a particular EPC page belongs to. The EPCM is also consulted during memory accesses to prevent EPC pages from being read or written by people who shouldn't be able to read or write those pages. So what kind of bits do we have there? The most important bits are the second one, which basically says, what is the enclave that owns this particular page in the EPC? And then also, what is the virtual address that this page should be mapped to in the untrusted host process? And as we'll see, this base address here is going to be used to kind of treat the EPCM as like an inverted page table to make sure that there haven't been any tamperings with the mappings between the virtual address at which EPC pages should live at and the physical address where they actually live. Okay, so here's how you actually build up an enclave. So in normal system memory, you have the plain text code and data for the enclave's initial state. So this will be sitting somewhere in regular system memory. This is going to be before eCreate happens. So eCreate is sort of the instruction that gets kicked off to start building up an enclave. So then what the OS will do is it'll call eCreate one time. And I put some sort of details sort of in the lower left-hand corner. You can sort of look at these details later on once you look at the slides offline. But suffice it to say that eCreate is basically going to generate a new SECS page. Think of this as like a metadata page for the enclave, which contains a bunch of bookkeeping information. Then you're going to do an EAD. By you, I mean the OS. So all of the instructions that sort of set up an enclave, these are all privileged instructions that only the kernel can execute. So after an EAD happens, what does that do? That takes a page of code or data from normal system memory, copies it into an EPC page. It's called a reg page, a regular page. But this is going to be used to start initializing the code and the data for the enclave. Now this eExtend thing is very important. So what eExtend is going to do is that it's going to basically hash some of the data that was added into the EPC. So as it turns out, EExtend only hashes 256 bytes of data. So if you have a 4K page, then the OS has to call EExtend 16 times to update this cumulative hash, right? So why is this cumulative hash useful? Well, we're not going to focus on this too much today, but it's helpful because of remote attestation. So essentially at a high level, once an enclave is up and running, a remote client might want to verify the identity of the remote enclave before sharing sensitive data with it. So what the client can do is ask the SGX hardware, which is assumed to be trusted, right? That's a very important aspect of SGX. The hardware is assumed to be trusted, even though the OS and the data center operator may not be. So what a remote client can do is ask the SGX hardware to essentially generate a signed message, which says, here is the cumulative hash of all of the data that was used to initialize the enclave. So both static data and the code as well. So that's what this EExtending is doing. It's building up this cumulative hash that will later be useful in remote attestation. So if you want to learn more about this, that's the keyword to look at, remote attestation. So as I just mentioned, that EExtend builds up this cumulative hash that can be used to attest the state. So why does EExtend only cover 256 bytes instead of a full 4K page? Well, hashing an entire page would actually take longer. And so that's kind of irritating from the architectural level, because if you have a long-running instruction, then it either has to disable interrupts, which seems bad because that means the system becomes less responsive to external stimuli, like IO events and timers and stuff like that. Or you can allow interrupts but fail the instruction or try to restart it somehow. But that's a pain if the instruction is fairly complicated, like a hashing thing. So basically what SGX does is it makes the EExtend instruction only cover 256 bytes. Then the kernel has to invoke it multiple times to cover a full 4K page. And as I mentioned, note that only a privileged code, that is to say ring 0 code, can call eCreate, eAdd, eExtend, and eAdNit. It is true that this means that the OS can launch a denial of service by refusing to load an enclave, or by loading the enclave improperly. So for example, by doing an eAdd, but not by doing an eExtend. And this is fine under the SGX threat model. Things like denial of service, it doesn't try to stop. And if the enclave has been loaded improperly, so eAdd was called too many times, not enough times, eExtend was called too many times, not enough times, that's also fine under the SGX threat model because a client can detect this via remote attestation. Let's see here. So there's a question. So if the private keys for the signature leaks to the public, the server could just emulate those enclaves? Yeah, that's a big problem. It's a big problem. And so people have actually looked at attacks that have sort of done that, sort of leaked those signing keys in some way, which then allows people to figure out what the keys are and then issue signatures for essentially fake enclaves. And so I'll mention a paper at the very end of this lecture, and you can look at some of the work this group has done at the University of Michigan. They've done some really great work on just this problem that you mentioned. Okay, so we do a bunch of eAdds and eExtends. We continue to add new pages, add them in the allocated state to the EPC. You can see that in the enclave page cache up here, we're also adding more valid entries as we do more eAdds of pages to set up the enclave. Eventually we create this thing called a TCS page. Like I said, you can look at these slides offline for more detail about that. Suffice it to say that an enclave can be multi-threaded. So this TCS page, it's a thread control structure. And this allows the enclave to keep track of how many threads are active and where they all are at in terms of like their execution status. So finally, the kernel calls eInit, and now the enclave is actually finalized. So now there can't be any more additional updates to the enclave state. And so if you want to enter into an enclave, use this eEnter instruction. roughly speaking, it takes in the address of the thread control structure that you want to jump into. So it's going to check the thread control structure to make sure that basically the untrusted host is not currently executing this thread. It's then going to flush the TLB entries because we don't want the malicious OS or malicious user mode process to somehow have filled up the TLB with mappings that are not the correct ones for this enclave. We're then going to flip the is enclave bit to 1 to indicate to the SGX hardware, yep, we're now executing enclave code. We're going to save the RIP, the stack pointer, and the break pointer to a scratch area that's inside the enclave's address space. This will be helpful when we're trying to return back out of the enclave. We're going to save this thing called the AEP, the asynchronous exit pointer, that's going to point to a location in the untrusted host. And basically, the AEP allows SGX to handle a scenario wherein enclave code is executing and then like a timer interrupt comes in or something like this. So you basically need a way to vector control to a known place in the untrusted host so that the untrusted host can then eventually restart the enclave by calling EENTER again, for example. So then what EENTER is going to do is write the address of the instruction after EENTER to RCX. And so this value should be saved by the enclave code. Once again, this is going to be helpful when we're trying to exit from the enclave. Then we're going to jump to the enclave start address described by the TCS. So at this point, we are now executing in enclave mode. The is enclave bit is 1, and now all of the enclave pages can be accessed by the core, as well as all the user mode pages inside the untrusted host. So you can do an exit, which kind of does the expected thing. You flip is enclave to 0. You flush the TLB entries. Once again, we don't want to reveal anything about memory mappings via TLB entries that would persist across the exit. You clear the TCS is busy bits. That indicates that this thread, this SGX thread, is now not being used. And then we jump to the jump target in the untrusted host. And so this should be the address that was saved by EENTER up here. So that's how that works. And so note that EENTER is only callable by ring 3 code, and you can't be in the enclave already. And EEXIT should only be called by ring 3 when you're inside the enclave. And another important thing to mention is that neither of these instructions changes CR3. That's important, right? Because the enclave lives inside of this untrusted host address space. It's just that when the is enclave bit is 0, the core can't actually touch these enclave pages. So how do we enforce that property? Well, this gets to this topic of the memory access checks in SGX. And so SGX is going to add extra hardware to the memory controller to ensure that these EPC pages can only be accessed by enclave code. And in particular, the particular enclave that is associated with each one of these EPC pages. And so this extra hardware is going to mostly rely on the EPCM, the enclave page cache map. And so if you remember, I had said that inside each one of these EPCM entries, there's this base virtual address of a page, and there's this owning enclave ID. So why is that helpful? Well, there's this very sort of long memory translation process that has to take place. But long story short, the way to think about this sort of complicated diagram here, which is showing how a virtual address is translated and checked to see if it's in an enclave region. Roughly speaking, look at this node right here. So basically we're saying, is the physical address that was generated by the standard page table walk? Roughly speaking, think of all of this stuff over here to the left. This is the regular page table walk that the chip would do. And so if the regular page table walk says, is the physical address in the EPC, does it belong to an enclave? Then what SGX is going to do is it's going to come alive now. It's going to say, let me do these EPCM checks. Are we in enclave mode? Is the current enclave that's executing the actual owner of the associated EPC page? We can check that by looking in the EPCM, right? Is the mapping that that basically took a virtual address to go to a physical EPC address, is that mapping correct? We can check that mapping is correct because we have the base virtual address of that EPC page right here in the EPCM entry. And so we can do all those checks. We can make sure that the OS didn't, for example, try to mess around with page tables to map an inappropriate virtual address to an EPC page. We can make sure that an enclave isn't trying to access an EPC page that belongs to someone else, so on and so forth. And so if all of those checks are successful, we allow the access to occur. Okay. So now let me describe just over the next 2 slides why SGX is vulnerable to some types of side channels. So the first thing I want to talk about is hyperthreading based side channels. So before we can understand that, we first have to do a little bit of deeper dive into sort of what processor architecture looks like. So here's sort of like a high level overview of what a hyperthreaded processor might look like. So the basic idea is that we have what looks like to software 2 separate pipelines. Okay, even though there's only sort of like a single a physical core. So 2 logical cores, 1 physical core. And so from the perspective of software, why does it think that there are 2 pipelines? Well, it thinks that there are 2 pipelines because we have essentially 2 sets of registers that are exposed by this single physical pipeline. So we have 2 sets of registers, 2 sets of execution state that can be scheduled by the OS. And so in this case, I've color coded the threads. So there's a blue thread that's operating on this top logical processor, and there's a yellow thread that's executing down here. So instructions get queued up. We go through register rename. We hold the rewritten instructions here. And then we get to instruction scheduling. And so what we see is that at this point in the core of the pipeline, this part of the pipeline is actually agnostic as to which logical core instructions come from. So basically what this sort of out of order execution core sees is just dependencies between various instructions in various registers in various memory values. There's not really a notion of, oh, well, there's this blue instruction with blue registers, this yellow instruction with yellow registers. I've color coded it here to make that clear to you as the human. But inside here, the core doesn't really care so much about that. Now, at the end, when we retire stuff, that's where we do have to care again about this notion of there actually being these logical cores. So here we see this reorder buffer. So this stuff in the middle here is out of order execution. But to enable precise interrupts, we have to retire each one of these instructions from each one of these logical cores in logical order. Okay, so we have out of order execution in the core, in order retirement here. So now, imagine that the blue code belonged to enclave code, and imagine that the yellow code belonged to non-enclave code. So what might happen here? Well, what's interesting is that there's actually contention in the shared core of the pipeline. There's contention because there are functional units and other resources that are shared between enclave code and non-enclave code. So as sort of like a trivial example, suppose that the non-enclave code wanted to determine whether the enclave was executing integer instructions or not. What the what the non-enclave code could do is just start timing how long its integer instructions take. And so whenever the non-enclave code sees the completion time for those instructions go up, for example, if you're reading the timestamp counter or something like that, then the non-enclave code can basically induce, it can infer, excuse me, that the enclave code is using integer functional units. So that's a side channel, right? And there's been a lot of work that showed how these types of side channels can actually leak a lot of information. For example, if the enclave code is performing cryptography, right? There's been a lot of work which shows that if the non-enclave code knows which crypto library the enclave is using, then based on contention for functional units, the non-enclave code can guess what keys are being manipulated, for example. So that's a very sort of powerful attack. SGX is also vulnerable to cache-based side channels. So if you want to know more details about this, check out the Foreshadow paper. It's a really cool paper. The details are very interesting. You can understand most of them, but there's some low-level sort of specifics that I don't want to get into. But here is a high-level overview of how this stuff works. So the enclave and the untrusted host process share the same L1 cache. Well, why is that? Because they're in the same address space, right? They're running on the same core. So they share the same L1 cache. So the untrusted host can do the following. It can load the enclave and then evict all the cache lines belonging to an oracle array. We're going to see why this array is called an oracle array in a second, but suffice it to say that there's this array, it's living in the untrusted host. The host is going to evict all of the cache lines belonging to that array using an instruction like CL flush, cache line flush, and then it's going to load the enclave. Then the untrusted host process is going to wait for the enclave to bring a clear text secret value into the L1 cache. Then the untrusted host code is going to do the following at a high level. It's going to try to dereference a secret pointer. Note that this secret pointer here, it's pointing into enclave memory. Okay, it's pointing into memory that the untrusted code should not be able to read or write. So the untrusted code is going to get a pointer into the secret enclave memory, dereference that pointer, get that value into V. Then the untrusted code is going to try to do a read of this oracle array here based on the value of V. Okay, so depending on what value V had in the enclave, that's going to determine which of these oracle addresses are attempted to be read, right? Now remember that in this first step up here, the untrusted host had evicted all the cache lines belonging to this oracle array. This is interesting. So you might think to yourself, well, but this isn't going to work, right? Because we know based on the way that SGX has described its security properties that this read can't work. We're not going to expose secret enclave memory to the untrusted host. That's kind of true. But what ends up happening is that even though the read will fail at the ISA level, so in other words, at the ISA level, you know, if this variable here is kept in some register, then the value for this read is going to be that dummy value, -1. So the read is going to fail at the ISA level. But at the microarchitectural level, there can be out of order execution. And so there can be a speculative load of this secret pointer value here, the thing that's being pointed to by that value. The CPU can speculatively execute that load, bring a value into V, and then try to read the relevant line in Oracle into the cache. All this can happen speculatively as the processor in parallel is thinking about things like page table protections and whether or not this load should actually be allowed to take place. So this is very interesting, right? Because this means that even though the ISA level read of this value failed, and this value here, V, will get -1, depending on how some of these microarchitectural race conditions resolve themselves, it could be that the speculative code gets far enough as executing this read here, bringing in a particular cache line in the Oracle array where that particular line is chosen based on this value of V, which is never revealed at the ISA level, but which may have side effects at the microarchitectural level via the cache in particular. And so what the untrusted host can do is that the untrusted host can then time how long it takes to read each of the cache lines in the Oracle array. And by doing this, the untrusted host can actually determine the value of V. Because remember, all the way at the beginning, the host evicted all of the Oracle array's cache lines. So if at the very end down here, the untrusted code reads each of those cache lines, some of those reads are going to be very slow. In fact, all of them will be very slow, except for the one that was brought into the L1 cache via the microarchitectural level speculation. Okay, so this attack is super fascinating. It shows all the challenges that are involved, with trying to reuse some of this legacy microarchitecture, like the caching approach used by X86. It shows how contention there can actually leak secrets from an enclave to the untrusted host. So if you're interested in this, I encourage you to check out the foreshadow paper. It's super interesting. I will also shamelessly plug some of my own research. This is a paper that we published at Hot Cloud, which will be coming out next week, actually. And so in this paper, we actually look at some different mechanisms by which we can provide SGX style isolation, but by sort of eliminating some of these side channels. And at a high level, the way that you eliminate side channels is very straightforward, right? You eliminate side channels by removing microarchitectural level sharing. That's very easy to state, but if you do this in sort of the naive way, you end up adding a lot of die area, and you end up adding a lot of power draw, because you're duplicating a bunch of stuff that used to be shared. So you sort of trade off sort of like lack of side channels for, you know, increased die area, more power draw, so on and so forth. And so in this paper, it's a workshop paper. This is currently stuff that we're looking at right now, but we look at some of these trade-offs and propose some interesting new architectural approaches to provide SGX style protections, but without the side channels. And we also addressed another important sort of deficiency of SGX, which is that SGX, it protects an enclave from untrusted external software, and it protects the memory pages from the physical data center operator who has control of the actual physical machine. But SGX enclaves actually don't end up getting protected in any special way from things like buffer overflows. So it's still possible that you could, you know, if you're an attacker, you could feed an enclave a malicious input and then use that malicious input to corrupt the control flow. Try to launch a ROP attack, stuff like that. So one thing that we look at in this paper that I'm showing you here is we look at, well, how can you provide SGX style enclaves with dynamic integrity? In other words, integrity that goes beyond just the integrity that attestation provides you. Here's the set of code and data that you loaded at the beginning of the enclave's lifecycle. We want to look at things like enforcing type safety, enforcing CFI for an enclave during its lifecycle. And so we have some ideas involving essentially secure coprocessors that basically allow a small monitor program to look at the state of a secure computation and run dynamic security checks on it to make sure that it hasn't been corrupted via control flow integrity attacks or type confusion attacks or things like this. So if you're interested, check out that paper. Anyways, we're now basically done. So what did we learn over the past 2 days? We actually covered a lot of ground. So on the first day, we looked at an introduction to control flow integrity. We looked at an overview of how virtual address spaces worked. We realized that, you know, page table-based protections, they protect one process from directly reading or writing another process's state. However, page table protections don't prevent a process from corrupting itself. And so we looked at a couple different ways that a process might corrupt itself. We looked at traditional buffer overflow attacks. We then looked at return to libc attacks. And then we examined a bunch of defenses. So no execute bits, Intel shadow stacks, and address space layout randomization. Today, we looked at some more advanced attacks and defenses. So we looked at memory vulnerabilities, both read and write, that can be caused by type confusion. We looked at ROP attacks and JOP attacks. All of these things are designed to allow us to try to corrupt the program, despite the fact that there may be defenses in place, like no execute bits. However, we also looked at some additional defenses. We've looked at compiler enforced CFI, which can be enabled by Intel's indirect branch tracing. And we also saw some pretty cool empirical results that show that actually it does seem, empirically speaking, that attacks are getting harder to launch. So, you know, sort of the very simple buffer overflows that we started with on day one, you essentially don't see those in the wild except for with IoT devices or code written by particularly bad students. So now attacks are having to get more sophisticated. So that is encouraging to see. the bar for difficulty of exploiting systems is getting higher. And then we ended with the discussion of SGX. As I mentioned, I think that hardware-based security mechanisms, I think this is the future. I think this is going to be a really important area for subsequent research. And so we talked about how SGX worked, and we talked about some of the vulnerabilities there. And so with that, I just want to thank everyone for showing up to the class and asking great questions. I know it was sort of like it's a long time, you know, 2.5 hours across 2 days, but thank you for showing up. Thank you for paying attention. I want to thank the organizers of the summer school for giving me this opportunity to teach this class. And with that, yeah, everyone stay safe out there, and I hope you have a great rest of the summer. Take care.